Right, so yesterday I finished by explaining or talking about some of those non-standard recombination models. I briefly spoke about decaying and annihilating particles and magnetic field heating and variation of fundamental constants. These are some of the examples, and you can of course think about other cases where you inject photons and then in that way, for example, excite and ionize the medium in a very specific way, which is beyond just this dark matter decay or annihilation. But today I want to really go into the codes. So I will really first start by just comparing those codes. So here's just a itemized list comparison of 3 codes, RegFast. So the original code that Douglas Scott and Sarah Seeger and Sasolov developed, then RegFast++, which is basically a version that I wrote, just updating and also simplifying a lot of the aspects, and then CosmoRec. I will also mention HiRec in the next, after this, of course, but let's just really briefly look at this. So first of all, you can compare, of course, here, this is still old Fortran 77 and 90, and there's also a C version, which unfortunately doesn't work anymore, so this is not updated. And in CAMP, there is a copied version of RegFast inside the CAMP itself. These 2 codes, they are written in C++, although RegFast++ is not using as much of the C++ object-oriented capabilities, so it's really kept very simple. There's no requirements for RegFast and RegFast++, but here for the CosmoRec, you need to have the standard GSL library. And there's also a feature related to showing the radiative transfer solution in real time, which I will try to illustrate later, which is depending on the Grace library, which is just a package which allows you to, basically play video. For RegFast++ and RegFast, there's only 3 equations inside, which are being solved, which is the proton number and the neutral helium, basically ground state population. And the electron temperature. I told you on the first day when I derived the RegFast equation, it's really nothing else than these very simple equations, and there is a cooling equation for the temperature as well. The same here is true here, although it's really easy to add additional equations. So for example, the version of RegFast++, which you should have been able to download from the Dropbox, has just solves simultaneously the cosmic time as well, because that is needed for decaying particles, right? So it's really easy to add some equations. And CosmoRec, depending on what kind of setting you use, solves several equations in addition. In particular, it solves specifically the 2s and 2p population as well for hydrogen, and also the equivalent for the helium recombination process. And depending on how many shells and how many of the resolved states you're including, so including 2 photon decays and Raman scattering, you can include 3s, 3d, 4s, 4d, and in CosmoRec, you can, for helium, for hydrogen, you can go up to the 8 shell resolved sublevels. The ODE solver here is an explicit solver, which makes it very, very cumbersome to use because the system you're solving is very stiff. So stiff systems, normally when you use an explicit solver, you have to take very, very small time steps. And in fact, there's several switches inside RegFast, which allow you to, here's an analytic approximation, which is getting rid of the stiffness. And then you switch to the real ODE when it's starting to become less stiff. And the solvers in RegFast++ and CosmoRec are both implicit solvers. They're based on the Gears method. And so these, you don't need any switches anymore, of course. The approach of getting the right result, and I will explain this a little bit more in what follows, is fudging the derivatives. So you have the equation for the ground state population for hydrogen and helium, and you compare with the full recombination calculation, and then just say, well, if I want to match that, I need to fudge the derivatives to get that. And here, in RecFast++, you're using a correction function approach where you're basically multiplying the solution by a correction function which gives you the right solution, calibrated on that cosmology which is using. And CosmoRec, of course, does the full physics depending on what kind of complications you add. This is rather simple. This is definitely simpler. I hope I can convince you. This is a pretty massive code in the sense of, yes, please. So when you do the analysis with Planck, you will find a set of parameters. Let's say you're using the wrong recombination code or an old version of RecFast for the analysis. You will get some set of parameters, and then you run with those parameters the full code, and then you know what the correction is with respect to what you have been using. And that correction function can then be added and multiplied basically to the RecFast++, and in that way you can then match the solution. And the next iteration would be a correction to the correction, which is, because we're talking about percent level corrections, as I explained yesterday, this is not very severe. But this, in fact, has not been demonstrated before actually being able to really run the full calculation in a quick way, because doing the calculation based for RecFast was, of course, time-consuming still, the full multi-level calculation. But thanks to acceleration schemes, you can of course run CosmoRec even on a case-by-case, and the differences are tiny. So if you're just one example, if you have helium, if you change helium by quite a bit, then you can actually see differences between the calibration of RecFast++, of these codes, which is used, versus the full calculation. If you go to cosmologies which are far away from the cosmologies that you normally expect, you again would be seeing some small corrections. But any cases that we have been looking at, there's no issue when you calibrate to the leading order correctly. But you can imagine an iterative scheme as well. Now, again, to some extent, I shouldn't even be saying that. I should just say, use RecFast, use CosmoRec, or HiRec, because the calculation is really taking 1 second only. You can do the full calculation, and you don't have to worry about this then. Yeah. Now, you can break those codes. If you go extremely far away with strong dark matter annihilation or decay, you can, in principle, run out of the regime in which these codes are actually able to solve the problem. But it's normally just depending on extending some of the tables which are used for the generalized functions. Yeah. All right. So. But this code, and I will try to show this as well, it has a lot of routines inside which you can use. This is quite limited because the flexibility, because you have to actually update derivatives and all kind of things, where here it's very easy to just add equations or change the equations, and you don't have to worry too much. And this code is very flexible, but it's much more interlinked, and it's a little bit more complicated to actually play with. I already mentioned it's valid for the standard cosmologies, and this one is, of course, valid for a wide range of cosmologies. What actually is tested as well. If you go to extremely distant cosmologies, you can still solve it, with many sigma departures from the standard cosmology. These codes, they have several tools. So this one has the ODE solver, which is, I think, very general. You can actually just, it has been done, just take it and it solves your ODE system. It's a stiff solver, and it's very easy to use as well. And this one, CosmoRec, has a hydrogen and helium atom inside. In fact, it is the full hydrogen and helium atom that I was using for any of the calculations of the spectral distortions and so on. You can get the transition rates between, if you want, a level 1000 or whatever you like. It's just, you can just directly use it. You can even get quadruple transition rates, and all these things are there. And there's already some extras here in CosmoRec and RecFast++. I told you already yesterday there's primordial heating, primordial field heating, magnetic field heating, and variation of fundamental constants and decaying particles. These are already implemented in RecFast++ and CosmoRec. Whereas in RecFast, it is very often just people have their own implementations and modifications. In the runtime, depending on the setting, CosmoRec can get actually quite expensive. When you do a full helium radiative transfer calculation, just to check, it can take 30 seconds if you really do many levels and all the feedback processes and so on. But luckily, for the calculation which are needed for analysis of Planck, it is in the ballpark of 1 second runtime. All right, and then of course there's HiRec as well, which is written in C. It's similar to CosmoRec, but it has it doesn't solve helium recombination fully. It just uses an approximate scheme there, and a lot of things are really pre-calculated. So modifying and generalizing it is not as easy. For example, there is no real hydrogen atom or helium atom there, and you can't really play with extensions. But of course, Yassine is extremely quick, and whenever you have a question, in principle, he will probably be able to add something, a feature, quite quickly. And then there's also older schemes, RICO, which we in fact used back in the days to estimate how big these corrections, what the impact of these corrections could be, which was just using brute force, running my old code, which was slow, but you could just do this on parallel, brute force parallel, and you just run it, tabulate, and then you have a high dimensional tabulation of the result, and then just run the parameter estimation of this. This is in the same philosophy as PICO, maybe some of you know. Even CAMP, some people can complain 8 seconds per model, or when you do very high precision, it can go even higher. People just tabulate, and then PICO is the scheme to do this. But this one is not really used anymore, and Ben Wandelt, in fact, was also involved in developing this, and he's one of the people who developed PICO. All right, so I told you yesterday the differences between all those codes. The main codes and RecFast++, I could add here, they are in agreement, in very good agreement. So we are not biasing at least the analysis of Planck data by any significant amount. Right? So we're happy with that. And here's just RecFast. I think I mentioned most of it, and in particular, it is part of CAMP and class, just a copy of the file. It's one file with everything inside. And the ODE setup, and then the derivatives of the ODE problem, and so on. You have to you have to look at all of those, and most importantly, it really fudges the derivatives and uses the full calculation like CosmoRec. In fact, it was using CosmoRec to fudge the problem. And initially, RecFast was actually only having one fudge factor, so just the hydrogen recombination rate was multiplied by a factor of 1.14 to just increase the recombination rate a little bit. And nowadays, because of all these radiative transfer corrections, it has a fudge function for the derivative. Yeah. So derivatives are being fudged, right? And this is just a reminder of this is the system that is being solved. I showed you this equation. I derived this for you. So it's just written in a slightly different way, but it's basically the same thing as I wrote, where you can see this 1 plus kappa, lambda, and so on, divided by this. This is the inhibition factor that I mentioned. Yeah. So it's the same as this. So this factor C. This 1 plus kappa and so on, and here 1 plus kappa in the denominator is basically nothing else than a tot, and then plus the recombination photonization rate from the second shell. Right, and then here the helium equation looks very similar. I didn't do the derivation. And here's the equation for the evolution of the matter temperature or electron temperature. So the assumption is that the protons and alpha particles and electrons, they all have one temperature, so that's why it's called matter temperature. And then there's the term coming from the Compton cooling, just the bulk interaction with the CMB black body part. And then there's the Hubble cooling term. Right, and here's again the equation that I wrote yesterday, just for a reminder. So the way Request is run, I'm not even going to compile it because on my system I don't even have Fortran compiler anymore. But you know, it has some simple setup routines, and you can also find in the Request code some mentioning of what these kind of corrections or switches that you can activate, what they mean. But again, I invite you look at the Request Fortran code, and you will see it is, you know, it's quite difficult to identify where things are and what is happening. So I'm not going to play with it anymore, but just go and show you as well that Request, in fact, as it is, there's many things that, or there's things that can go wrong. One of them is connected with the primordial magnetic field heating. Yesterday I showed you this figure, but I didn't explain what I'm actually, what these different lines mean. So here's the standard recombination history, and here's the Cosmorec and Request++ result when you have the heating switched on due to magnetic turbulence. Yeah. And you can see here that when you do these the cases with Request itself, you would actually get a far bigger effect. And this is something that was actually happening in the original evaluation by Kerstin Kunze and Eiichiro Komatsu, because this factor, the most important aspect is that in Request, the equation for the photonization here uses the matter temperature. But the photonization rate is driven by the photons, which means the photon temperature should be there. And it is an obvious thing, but not, the approximation which was done is that the photon and matter temperature are the same, basically, which at the late stages is not true because the Compton cooling and coupling is becoming inefficient. So that's why you get this quite significantly larger effect, because when you make the electrons hotter, it means the photonization rate at that electron temperature would, of course, be increasing, and that means they are pushing into the continuum much more. Whereas the real effect is photonization rate doesn't change, but the recombination rate is slowed down. So you get a delay of recombination as expected, right? Because the faster electron will not recombine as easily, but you don't get the enhancement of the photonization rate, which leads to another factor of 5 increasement here. Okay, so that's where just to caution, it is good to look at the full calculation sometimes and actually check if you can actually get the right results, even in your non-standard models. That is not to say that Request++ is unbreakable, because of course it also uses approximations, as I already said. And the way the corrections are done, and I mentioned it, is just you do the calculation for the full calculation with Cosmorec, and then you look at what Request++ would be producing, and then you have the correction function. You just multiply your solution by the correction function. And this correction function is precisely the function that I showed you yesterday. And the nice thing is, of course, that if somebody updates the cosmology, or if somebody updates the sum of the physics, you can just run this code, replace the correction function file, and you're done, right? So it's very easy, whereas in Request++, there's a lot of fiddling, Request, there's a lot of fiddling going on there, and it is a little bit cumbersome. We have now, in particular for the variation of fundamental constants, Luke Hart and we have actually included correction functions independently for the helium and hydrogen recombination part, because you want to make sure that things are matching in the right way, right? So this is rather easy to do. And you can download Cosmorec and Request++ on my webpage as well. Although the code that I put in the Dropbox, the Cosmorec code, is still the version that is actually available here. But for the Request++, I gave you a greatly updated version to play with now, because I didn't have time to really update this on the distribution. So breakfast++ had a similar, just in the same philosophy, old school, here's a file with numbers and here was some explanations, but I finally updated a little bit, so I replaced this by something which has a real full parser, because, evidently that is a little bit difficult to interpret. So here you have now parameters, and you can see what these mean immediately, and we will be looking at some of the non-standard cases. So here's, for example, parameters describing the variation of fundamental constants, and you have different ways of switching them. So this is rather easy to use and just play with, and modification is also quite easy. Breakfast++ can be called from within CosmoRec, just by, instead of just calling CosmoRec with the parameter file, you add here these small little additional flags, and then you can, in principle, run recfast, the equivalent of recfast, and the equivalent of recfast corrected as well, with the same settings that you're using for the CosmoRec files. CosmoRec has its own parameters, and I will talk about them a little bit in a second as well, but it has the similar main features, although here I have not yet updated the parser. It's one of the steps that Luke is now doing, and we will hopefully clean up and make CosmoRec much more simple to use in addition. So CosmoRec is really, I already mentioned, is quite flexible. It uses the multi-level, effective multi-level approach that Yassine, Ali Hamoud, and Chris came up with, and I'm going to explain this in a second. It's pretty quick, and it does the real radiative transfer problem of Lyman alpha, Lyman series, and also the equivalent for helium. And I hope I can illustrate this a little bit. Extendability is pretty high, and it is already part of CAMP, and also class has now added CosmoRec as an option, and it has been used for the main analysis of Planck data. So the most important step in terms of improvements of the recombination codes, making it possible to really calculate the recombination history case by case in an analysis, was bring down this a long time runtime with 500 shells or 300 shells, which took like a day or something in the most recent brute force codes, 2 seconds, right? And this is of course a really cool step. It didn't add anything in terms of the physics and the solution. The solution is equivalent. But the nice point is, and this is something that Yassine figured out and worked out. So Yassine, whenever some code is not fast enough, just go to Yassine. He will figure out how to make it really quick. Okay. It's also the same with the recombination spectrum. You can calculate the recombination spectrum in 15 seconds now, because you can effectively integrate out the higher levels. So how does this work? So we want to describe how the ground state of hydrogen is increasing. The population is increasing because of recombination. And I told you, you have to think about the 2s level and the 2p level, right? Maybe the 3s level, 3d level, and so on, right? And so there is some states which are dynamically coupled to the ground state. These are the s levels, right? Through the 2-photon decays and Raman scatterings, and the p states, and then also the d states. Yeah. So these are what Yassine calls interface states. I call them resolved states in my papers. It's just meaning that you're actually following the levels of these, the populations of these levels explicitly. Right? So every population then means one equation, but when you go only to 5th shell, you're talking about a couple of equations, right? Or when you go to the 8th shell, it's not many equations. And then the other levels, they are not directly connecting to the ground state, or you're not interested in their direct connection to the ground state in a really precise way. And then that means all that these levels are driven by, they are by the photons, because CMB photons, black body photons, there's no distortion in these cases. So, for example, the transition from the 2nd shell to the 3rd shell by a Lyman, by a Balmer alpha line is really just black body photons. And of course, because of recombination rates and so on, they are determined by the electron temperature as well. So that means these higher levels, which are called interior states in Yassine's language, I call them unresolved states because they're not following them explicitly, can be integrated out. you can basically do the big matrix inversion before the calculation, and the result of this big matrix inversion is then just a two-parameter table, right? The temperature of the electrons and the photons. And because the electron temperature and photon temperature can depart from each other at late times, you need to do that carefully. But when you do that carefully, then you do the hard part of the calculation once, and then you can just run the rest quickly. Now that means that when you want to do, let's say, 500 shells or 200 shells or 100 shells, you need tables for each of those, because of course the physics is different when you increase the number of shells. Right? So in the CosmoRec version that is the big version, you have several of those tables just to play with, and the one that you have is indeed including those. That's the reason why it was 20 megabytes or something like that, because it has several of those files. Okay, right. So CosmoRec specific parameters, there is things like the two-photon decay rate you can change, you have the dark matter annihilation and so on, but then in particular the recombination physics, and they are commented in the just depending on how many number shells you want to include for helium. There's also the number of shells for hydrogen. It's actually just a little bit earlier. I didn't show it here. And then you can decide if you want to include the feedback or the absorption process of hydrogen on the helium resonances or the feedback and so on. And that allows you then to decide what complexity of the model you want to calculate. And to some extent, of course, this is just for understanding the problem. The real solution, there is a setup which is just giving you the solution which is accurate enough for the calculation within Planck, for the Planck data analysis. All right, so I think what I'm going to do now, and I'm not totally terrible with time, I'm going to try to show you a little bit about how this looks like. So let's see how big this is. Of course, reading AstroPH is extremely important. Yeah, so you go to my page, right? And you go to the CosmoRec, and then you basically find this this information. So the codes are here. This RecFast++ and CosmoRec. They're explained. There's also, for example, the Lyman series transition movie, which I showed you in my lectures, and you can have a look at it. The RecFast++ code is just briefly explained and what it can do. And then here's actually one figure which illustrates how, and this is maybe, let's see if I can get this zoomed in. Oh, great. This is, for example, showing you that if you do a RecFast++ approach or a RecFast approach on the full calculation, but change here the temperature of the photon field, and in this case here even the abundance of helium, then the correction function is no longer the same correction function as for the standard case, which means that if you fudged your calculation in RecFast or also RecFast++ with the solid black line, then you will not predict the correct, absolutely correct result for the effect on the CLs, right? So this is just to say, when you go far away from the standard cosmology, then you will see changes, and CosmoRec is capable of including those. And the ones here in helium recombination, in particular, is RecFast++. CosmoRec, excuse me, is currently the only code which really does it. All right, so let me just give you a very brief, I should show you, well, the download section is also extremely simple, so you can in principle download. And just to show you, so I have a couple of old versions of CosmoRec in this, just folder, and for RecFast++, it is still an old version, so if you download that, it will have quite significant differences to what you have now downloaded, the RecFast++ version 2.0. All right, so installing should be fairly simple in both cases, CosmoRec and RecFast++. But let me just show you very briefly the structure of, maybe, let's see. Right. So the structure of the code is, of course, there's a header file in Cosmorec, which has just the main functions, and there's also some explanations for what these parameters, what the different run mode parameters and so on do. This is going to be updated. There will be just added a structure, and we will do that in the next update. But this is allowing you, for example, to include this in CAMP, and then just you run the code with different settings and pass on the parameters, obviously. There's yes, this is fun. Let's see if we can get this. Yes, there we go. Nice. Well, yeah, excuse me, it's a little bit small. There is a folder which is called development, and in that folder you can find all kind of tools which are in fact quite standalone. So there's a cosmology object there which has standard things like the Hubble rate and all these obvious aspects. There's the hydrogenic atoms, which is the guts of the hydrogen atom. So if you look at that, you get here the atom class, and then it has different dependencies on oscillator strengths and so on. You can just, in principle, go and include those files and just play with oscillator strengths or with transition rates directly. The similar thing is for helium. You have the helium atom. The helium atom is more complicated. There's this, as you can see, it doesn't depend on any data. It's just completely computing everything internally, whereas the helium atom has some dependence on certain data files, and it depends as well on what kind of version of the helium atom you're using. So it's a collection of approximations as well, whereas this is really fully analytic. And there's quadruple lines if you're interested in this. And it's just all kinds of recurrence relations which are doing this. Then, this is interesting. Can scroll, great. Then there's just simple integration tools, but these are actually interesting because when I developed the code, for example, the GSL library didn't have things like the Patterson scheme and so on inside, and these are very, very highly efficient quadrature rules which are fully nested. So this was quite useful because the recombination rate calculations were really accelerated by using this kind of schemes. So you can, in principle, find them and play with it. There's the line profiles, which are connected with, for example, the two photon decay rates and the Raman profiles. Simple functions in there where you can just plot the Raman profile itself and so on. So you can, in principle, do all those figures if you wish. And these are again with minimal dependencies on the hydrogen atom and so on. And I think one of the things that is quite useful and maybe worth pointing out, there's the ODE solver, which is, as I said, a stiff ODE solver. This is basically the version of the ODE solver with a little bit of downsizing that was used to solve 125,000 equations, right? So this is the solver that can handle these kind of problems, and it is fairly easy to use. You just have a couple of dependencies and setup of memory and so on you have to take care of, but then you can pass it on a function which defines the ODE set, and you can decide if you want to put a numerical Jacobian of the problem, or if you want to do a full analytic Jacobian, which in some cases is very helpful because, of course, numerical precision might lead to inaccuracies of the estimation through numerical derivatives, and that means you get, of course, the results become more unstable. And there is a PDE solver, which is basically solves the radiative transfer problem. And that radiative transfer problem, a similar problem is also, for example, for my calculations of spectral distortions, I basically use augmented versions of these solvers. So in both of these solvers are quite flexible, and I remember when Marcelo Alvarez, he wanted to solve some diffusion problem, and it was asking me, and I said, yeah, try this and see, and he set it up, and it was no problem. So he was really happy because he had never done before PDE problems, and for simple diffusion equations and so on, this is really a quite nice tool. All right, there's recombination rates and all these things. Great. So the guts of CosmoRec in terms of the setup is in fact in these modules, and I call them modules because they're really basically nothing else than me trying to avoid that I have like one file which has like this long tail, but they are basically nothing else than sub files in the CosmoRec code. So this is really something which CosmoRec depends on directly, and I didn't make them independent header files because they are basically nothing. They're not useful for anything else than part of CosmoRec. There's, for example, setup routines for the outputs, where you can find what kind of outputs are generated. You can change in the run files. You can change or with the flags. You can change if you want to, for example, get the solutions of the highly excited states as well. It's just switching a couple of things on and off. It's really quite easy to do. In fact, you can find this directly in the CosmoRec header and play with that. The main call, so driver, is this main CosmoRec, where you do all the aspects of the calculation, and the ODE definition is done in this file. Yeah. So I don't want to really go into this because otherwise we will never get to RecFast++. But there is where you can find the helium setup, the hydrogen setup, and it's all pretty. I mean, you can clearly see what's going on. There's initialization routines. For example, here, let me just maybe briefly show this. That's fun. Right, so the hydrogen atom, of course, has to be set up, and you have to, depending on what you want to do, how many shells you want to include, you decide with the run files how many shells you have to include. You can also, of course, by hand change this, and it just says, okay, create the hydrogen atom object and include quadruple lines or don't, do some calculation of recombination rates or don't, and then you can play with this. So this hydrogen atom, which you then have, has all the capabilities of getting transition rates between levels and all these things. They are all there then. Yeah. So for example, here, if you, I was calculating one of the papers, I tried to calculate the correction to the lifetime of levels from quadruple lines. And of course, these quadruple transitions are pretty low probability transitions, but there is a simple routine set up which you can in principle look at, and you can get easily things like the transition rates by just in the object-oriented way, just the hydrogen atom and then corresponding functions which gives you transition rates. The structure of the hydrogen atom is that you have the whole hydrogen atom, which is thought of as a gas, where you have a temperature being characteristic and the shells and so on. Then when you go into one single atom, it has only, of course, shells and substates and so on. And then the shells themselves are built up as levels. So it is really the typical object-oriented way of thinking about a hydrogen atom. And when you initialize, you basically are just shoveling in levels into shells, and you're building up the whole atom, and that's how it works. Right. Maybe let me. All right. I should at least point out the. That was not what I wanted. Oh, come on. There we go. Right. I talked about this. I talked about the modules, and this is where the PDE problem is being treated. So CosmoRec does not have a solver which does the simultaneous PDE problem and ODE problem just exactly at the same time. The reason was development to some extent, because first I had the normal high-level calculations, and then the PDE problem was added later. And it is actually a good idea to do this in the way it is done here, because the PDE problem has much longer timescales than some of the level populations. And for the PDE problem, you have to solve many additional equations, which slow down the code quite a bit. So what is done is you run the code without the PDE problem, then you have a solution, and that solution is fed into the PDE problem to solve the diffusion of the hydrogen lines and the helium lines, and then you do one more iteration, and you can basically, or you can decide how many iterations you do, and then you get the final result in an iterative, corrective way. So the PDE problem, the most important part is where everything enters is the solved PDE setup, and there's the defined PDE problem where if you go in there, you can basically see here's electron scattering, here is line scattering, here's all these things, and you can play with that. I will also show in a second that you can actually change certain, you can define different outputs in this PDE solver, which are not at this point communicated from all the way above, on top, down. So there's actually features you can use and play with. And there is, of course, a similar problem for helium, for the neutral helium. And in my Cosmo spec code, which is calculating the spectral distortions, there's in principle a third PDE setup. Now again, there's a good reason to do this because the helium lines, they are the hydrogenic helium lines, they are active at very, very different times and in very different frequency regimes. So if you would, for example, solve the hydrogen and helium lines together, you would have a really, really large domain to deal with, or you should split it up into subdomains and then make sure that all the communication works. So it's much easier to, in principle, just split them up into different cases. And maybe one more word about the database. So here is in this in this file folder, you have the database for the effective rates. So if you want to change, if somebody wants to do highly, strongly dark matter annihilation or decay, and the tables might be not enough, then what you do is you basically have to update these tables. And excuse me. I already should have maybe, so in this one there's no table that extends to a very, very large range of dark matter annihilation rates. But you can see here these tables are basically nothing else than these effective pre-computed coefficients for the recombination rates, and you basically just interpolate on those. And depending on how many shells you include, you need different tables, right? Because when you do a setup with 3S and 3D resolved, that is a different physical combination than a setup with 2S and 2P only resolved, right? So for the standard calculation, usually going up to the third shell is enough. If you include the fourth shell, you get a tiny correction in terms of the sensitivity that Planck and CMB experiments have. But of course, there is a difference. You can actually notice the difference. And up to the 8th shell, the 2-photon and Raman scattering rates are included, or can be included. Right, and then finally, the run files, which, as I told you already in CosmoRec, these are not yet that beautiful. They're just simple, here's a list of numbers. Excuse me. Here's a list of numbers, and you can basically get the explanation below, and this just defines number of redshift points, the starting redshift, ending redshift, and so on and so forth, right? And you play, and here's, for example, hydrogen levels and so on. So let me just show you how this works. So let's go here to the standard default case. So make tidy is very helpful whenever you do something and you're not really quite sure why it's not compiling. But usually make should work when you're updating things. I should maybe, in addition, say this is one important aspect. So in the there's a make-file which is just the main make-file, and that main make-file just links to whatever platform-dependent settings you have, which is called make.in. And in there, you do have to specify properly where the GSL library is if you want to use this. So that's normally the only place where you really have to do something, unless you have more complicated platform dependence, which apparently for RecFast++ was even an issue. But if you have any issues, let me know, because then I can try to fix it, because it's, I haven't, of course, tested myself on multiple platforms. I'm just basically getting feedback from people, and then I try to fix it. There's a feature which we will use in a second, just because I think it's quite nice, which is this Grace library, which allows us to see the movie of the Lyman alpha transfer. So currently I've just compiled it with the standard setting, and it was all happy. And then I just run it by invoking, just pointing to the parameter file. Let me actually not do with helium diffusion right now, just a standard parameter file, which is basically the calculation that you would want to do when you do the cosmological parameter analysis. Now let's hope that it's not crashing. Yes. Okay. So what it did, and of course here you can switch off and on the outputs, but it did basically 2 iterations of the recombination problem. First solving the problem without diffusion, but with some new physics included, of course, then solving it with hydrogen diffusion and all these things, and then doing this another time and making the outputs. And then what you get in the output folder, but you can specify, of course, where it goes. You get these outputs, and just for reference, this is a little bit bad to see, but I'm afraid I will have to just deal with this. There's 4 files here now. The first one, where there's the ending is just XE, that is basically the 0th iteration without any diffusion. Then the first iteration of the diffusion, just for you to understand actually the physics, you can obviously switch this on and off. And then the full transfer calculation is the last file here, which ends with trans. And there's also always, for convenience, the recfast result given as a comparison, and this is the recfast old result, just for you to actually be able to see and appreciate the differences. So if we load, if we load the recfast, excuse me. So I'm using here Grace to just do this because it's the easiest, and you can just do directly. So if we load the file, and just plot the first against the second column, then we will just get, this is the recfast result for the ionization history as a function of redshift. That's just what recfast would have given in pre-2005, basically. And if you then compare this to the final, to the recfast Cosmorec output, then you see what I told you yesterday about as well, this big acceleration of helium recombination, right? Around a redshift of 2000. Yeah. So this is where all the hydrogen atoms which are there, although it's a tiny fraction of really neutral hydrogen atoms, that's basically still consistent with fully ionized, but it's at the level of 10 to minus 6 neutral. Those hydrogen atoms absorb helium lines, and in that way allow helium to go to the ground state and recombine. Yeah. So this is the recombination history change that I showed you in this one figure yesterday as well. So evidently I don't have really much time to go through different cases, but let's do just one simple one. First of all, let us switch on the support from Grace. So I don't want the helium. I already did a small modification just because I wanted helium as well. But let's just, no, I didn't. Okay, great. So now I do make tidy, in fact, because I just really fully have to relink. I added now the Grace library. Again, it's if you use Homebrew or Port on Mac and similar on Linux machines, you can just get this Grace library. Usually it's part of standard packages as well. I don't think there's any big issues installing it. But it's a really nice thing because it allows you to use what I'm using here for plotting in real time and just get the outputs. And the nice feature is, especially when you play with new physics or settings of the solvers, it's really, really helpful to look at this because you see immediately that there's numerical problems or whatever and where the problems might come from. So it's really helpful to have this movie. That's one of the reasons why I implemented it. Okay, this was happy again, so let's go. So now we do the Hydrogen recombination problem, that's how fast it goes inside. And the time extra spent now is creating these figures, right? So this was just really quick, right? It really solves here just 3 shells in terms of the resolved states. So it has Lyman beta feedback on Lyman alpha. Lyman beta feedback is the most important feedback on Lyman alpha because it is, of course, the most significant additional line and number of photons. In fact, I believe the correction is something like 0.2% on the hydrogen recombination history. If you do the feedback correction, it's something that we separately studied. And in fact, you don't if you want to have a rather precise description of this, you don't need to do the feedback correction, can be done quasi-analytically as well. But of course here, with the transfer solver, you actually get the full result. So I one of the things that I immediately did here, in fact, is I changed a small part of the setup of Grace, and I was really happy when Luke found out how to do this, because without this modification here, so originally it's just this line which is uncommented, without that modification, the window was not actually giving me the full window, so I was always like, how do I see the whole, and it depended on the platform and so on. So Luke was finding how to do this. I was not spending enough time. Anyway, that allows you to give the full screen result. And let me just do the same here for the helium recombination case. Clean PDE part, make yes. So now I activated the same movie capabilities for helium. And I haven't, in the standard calculation that I showed you, I didn't include helium actually right now in terms of complicated diffusion problem. So if I now just run this again, it should just show us the hydrogen movie, yeah, and twice, because there's 2 iterations of the PDE. If I, however, now do the case with helium, then I'm hoping that it won't crash, and it will show 2 movies now. So this is helium, yeah? And you again see this feature of where helium lines now start disappearing at late times. They just are erased because of this absorption effect, right? And you can also see, I don't remember if the setup actually shows the positions of the lines, but helium has three lines in the third shell. In the third shell. There's the quadrupole transition in addition, and the singlet triplet transition. So you have all those feedback processes and stuff like that taken into account. And when you do the radiative transfer solution, you have to at every time step integrate over the solution to get the excitation and de-excitation rates for the levels. So that integral is one of the things that takes some time to actually do, and there's even ways to probably make the code faster. I'm optimistic that one can probably get another factor of 3 out of the code runtime. And maybe then finally people will agree that running CosmoRec instead of RecFast is the right way to go. Maybe one more physics while I'm running really out of time. Let me, I will just point you towards it. In this start file, you have here 500. That means I'm using the effective 500 shell hydrogen setup, and you can change this number to 20, for example, or 100, and then you will see, let me even just do that really quickly. I just will do it with 20 now. The nice thing is, or some people would not call it nice and find it inconvenient, is that the parameter file changes normally are reflected in the quite long name of the output. So I can immediately see what was happening. So if I take here the 500 shell transfer equation, transfer result for hydrogen, right? And then I do the, excuse me. Oh, of course I ran the wrong file because I wanted to run the hydrogen standard case. So excuse me again. Now I'm doing the 20 shell calculation and hope that it's not crashing. There's always this nervousness a little bit. this should have now created some file where the file name contains explicitly statement of the 20 shells. So if I now take this output and just plot this, then if I make the y-axis logarithmic, excuse me, then you will be able to see and appreciate what I told you yesterday, that the red curve is lying above the black curve, which is just meaning that when you make the hydrogen atom bigger, you capture electrons more efficiently, so you recombine faster, and here the recombination rate is reduced, and you're not getting as high precision at late times. Now, the interesting thing is, of course, that at late times, the visibility is already quite small, so you're not sensitive to this as significantly as you are, for example, to tiny changes here, because you can't really see them even when you compare the rec-fast output. They are just percent level, as you understand. But here it's quite visible in logarithmic scales, at least. Reionization kicks in here as well at late times, of course, and this is something one can play with. It's rather easy to add this. I, in fact, have already a code which has a reionization module as well. All right, let's go to RecFast++, because I think this is probably the more likely code that are easy to play with. So let me just go here, make tidy. So this should be basically the code you have downloaded from the Dropbox, and it's only a small modification to the, in some cases, to the makefile because of some strange dependencies of the in terms of the machines. But again, you type make, and then something is not working. Why? What has happened? Oh, yes, I'm wrong. This is not the right folder. So because in the Dropbox you don't have make, you don't have the allowance to, or there's some anyway. So then make tidy to clean up the mess. And then make compiles things. Then I have my file. So let me just show you the structure of RecFast++ really quickly. Come on. Wait. I do this. I do this. Yep. Okay, fine. Zooming the screen is not that easy, but I think you can read at least a little bit better. So again, the RecFast++ just has a main header file where you find, the main entrance. There is here a main RecFast++ file, which is the driver file. I will show you in a second because I think it's nice to understand some of the structure. There's some run files, which we will look at, and there's the source code and the include files. So the includes are just different modules. So there's the constants, which are just really fundamental constants. There's cosmology, there's dark matter annihilation and decay module. There's the ODE setup and evaluation. There's magnetic field heating. So each of those physical processes is just a new file, basically, right? So that's rather easy to understand and localize. Some of these are being used internally, of course, as well. There's the parser, which I added recently, and I think it's a nice, it simplifies the reading, obviously. There's the cosmological, the variation of fundamental constants, and there's also the correction function module, which just allows you to load and unload all those correction functions that you want to play with. So let me just, so here the dark matter annihilation header is really trivially simple. So there's dark matter annihilation case, there's dark matter decay case, and here is actually the functions which are allowing you to describe how excitation and heating and ionization are fractioned into each other, how they are branching into each other. And we will maybe look at this if we have, if Rishi allows me maybe 10 minutes extra or so. And there's dependencies on all those things like the electric fraction and so on. Right, and outputs are not interesting. Run files, we will look at those. As I told you, they are structured in a readable way now, and one can just switch and change. And maybe the source is interesting. So if you really want to see So again, there's an ODE solver, the same ODE solver, but a little bit smaller version than in the Cosmorec case, but it's just a stiffly stable ODE solver, and that is, defined in this file. And then all those individual physical processes. But the main guts, the main driver of the ODE evaluation is in this eval ODE recfast file. And if you look at it, there's just simple things like, excitation, Saha, recombination rates. So instead of having tabulated recombination rates in recfast++ and recfast, you just have fit functions for these recombination rates. If you look at this function here and compare to the original recfast function, then this is exactly the same function which is given there. So it's just done here, the recombination rates and photonization rates. Then you go down and you have the evaluate ODE system. There's a couple of local parameters, and then there's nothing else happening than getting Hubble, getting the number densities, getting the helium fraction, and here the setup of the equations. The variables here is helium, the proton number, temperature of electrons, and then the cosmic time, because I needed that and it takes no extra time, obviously, to do this. And then a couple of additional dependencies. Here's, for example, the Compton cooling factor. And then the fundamental constants, they do require rescaling at several places in the code, but it is all handled in the the fundamental constants routines, but you still need to do certain rescalings of coefficients and get then the right result. Then depending on, I told you, the evaluation of the photonization rates in the with electrons temperature or with photon temperature, there is, of course, you can reproduce the old but quote-unquote incorrect result with the electron temperature, using the electron temperature, and this is just decided here. And then you define those inhibition factors, which is, basically, again, this thing, but here written in the original way with this kappa constants and kappa variables. It's also explained what they mean, not so difficult to see. And then here's our 3 equations for the recombination problem. And you can identify them quite easily. If you want to add another equation, you of course may have to make the setup routine realize that you have now 5 equations instead of 4. And all those changes are very easy to do, but in the main recfast driver, right? And then there's additional physics. So this is the standard. This is the standard part, and then you add here dark matter annihilation terms, or if you want decay terms or magnetic field heating, and then there's also the effect of collisional terms being included, in particular when you're doing strong heating rates. This is something that affects the results because the electron temperature otherwise would go very, very high, could go to millions of Kelvin if you have if you don't include collisional heating and cooling terms. This is another aspect of which is of relevance when you do non-standard models. Right, so then running, again, just like in Cosmorec, where you just make ++, run files, and then you decide, you do the standard case, and it runs really quickly and produces some outputs. It tells you what it did, and you can then, of course, plot things. But let me maybe show you how the dark matter annihilation and decay part works. So there is this is an approximate scheme. It's based on the at this point on the original paper by Chen and Kaminkowski, and Finkbeiner and Padmanabhan also used a similar scheme. In fact, most of the calculations are using basically this scheme, where you have to decide when you have an annihilation event, you're knowing that the release of energy is just it's great. Nobody started stopping me. So that means I still have 55 minutes. You know that when you have an annihilation energy release, then you just the mass of the particle, that's the energy per decay or per annihilation, which will be there. And annihilation goes like the density of the particle if it's self-annihilating square. right? And then you have to multiply this by the sigma v, which is nothing else than the annihilation rate. And the sigma v in S-wave annihilation is just a constant, just one number. And you can have P-wave annihilation, where you can have, depending on what kind of species it is, it can be redshift dependent, right? I think I might have even implemented P-wave, but I'm not sure. The way things are normally, what now is important, this is just the total energy, right? And you want to know now, how does this energy branch into heating, excitation, and also ionization. And these fractions are what is depending on the particle physics and on the medium ISM physics. And Tracy Slatcher and also people like Gattuzi and others have calculated those kind of branching ratios carefully, but in this code, and it's really easy to replace, obviously, if you have calculations of more or more specific redshift-dependent functions. In the current CosmoRec and RecFast, it's just modeled by an overall efficiency factor. So, for example, electron-positron annihilation, those channels normally have an efficiency which is something like 10% in terms of what fraction of total energy really gets into the medium in terms of like transferring its energy. It can go up to unity as well, but at late times in particular, it is not as large. And then you have to decide how to branch it into these different heating rates, and that is done in this module where you basically have to decide how this is branching. And here's branching ratios, and they are just defined by what Chen and Kamienowski used back in the days, and they are based on Scholl and von Sternberg calculations. And then you add those corresponding heating rates. Here it's written as a function of redshift, yeah? And it is also in CosmoRec and RecFast usually expressed as heating per hydrogen atom rather than total heating here. So you divide here by the number of hydrogen atoms and of course get the redshift is just 1 over h times 1 plus z with a minus sign. And then you also have a factor of, so let's call this per hydrogen atom. This heating rate is normally expressed in this way. And then you have the dE dt, which you have to set up. And this dE dt depends on what kind of particle you have, or what kind of case you have, annihilation and decaying particle. So this is the module that's just taking any heating rate and translating it into photonization, excitation, and heating of the medium. Right? So this is general. It's actually the same module that can be used for the heating, adding the heating from magnetic fields in principle. But there, it is really just heating, no excitation and no direct ionization. And then the two the two functions that are relevant for deciding annihilation versus decay, it's really trivial, because all that you're doing here, you're defining this efficiency factor, which is basically taking all those constants here, all those things, scaling out all the redshift dependencies, because this is overall going like z to the 6th power, right? Then you divide by Hubble. This is, you can see here, and here there's only 2 factors of z left over, because you have 1 factor of z here, and you divide it by the hydrogen number density at every redshift, which gives you another factor of z to the 3rd power, which means you have z to the 2nd power left. And then it's just multiplied by 1 efficiency factor, and that's how you then then you call the excitation ionization module, and you're done. And for decay, it's basically a similar philosophy. If you write down the dE dt, and this is again nothing else than the mass of the particle. So the energy which comes out, you're assuming that there's no real internal energy or thermal energy that is relevant. So you just have the mass converting into energy, and you would now just multiply by the decay rate, multiplied by the density of the particle, and in that way you will get what kind of energy input you have. And this solution for a given time, of course, is nothing else than some initial or solution that would be there if it wouldn't be decaying, right? Times 1 plus z. That would be the z to the third power. That would be the standard expansion scaling. And then you have another factor, e to the minus gamma x times t, the cosmic time. And that's the reason why I needed cosmic time, because if you have a decay of a particle that is short-lived compared to the lifetime of the universe, you do need to have this temperature, this time, cosmic time, to really evaluate this, right? And that cosmic time, of course, depends on what cosmology you use, and so you just integrate this. And you can see here, let's do the same thing. There's basically an overall efficiency factor, and here it is expressed with respect. So there is a, I even allow, what is there a fraction of cold dark matter, which fraction of cold dark matter could be decaying. That's just to say that if you have excited states in dark matter, that would be 100% of dark matter could be decaying, but it wouldn't actually mean that dark matter is disappearing. It would just release this internal energy in that sense, in form of photons, let's say, or some other interaction. And then you have nothing else than, you know, the decay rate, and here the time dependence, just according to this, and then 1 over Hubble and 1 plus c. So it's all pretty obvious how this works. And let us just run the code. Let's do a decay case. I don't know which one I set up, but let's do it. Okay. So if I now go into the folder where those outputs are generated. So I go to my Recfast++ folder, and then in the outputs part, it will be evaluated. I have here, again, the standard case, but that's just a residual from some previous calculation, I believe. So here's the output that was generated for dark matter decay, and let's see what scenario I was picking here. Let me just plot this. No, yep. Oh, great. So I made a scenario where you have actually quite some decay at late times. And I want to do this in log. So you see the decay was really pre-ionizing the reionization part of the history, basically. And if we look at the parameter file for this case that was used here, so I'm doing here decay. The only thing that really changed is, of course, the decay efficiency. So I just switched this from 0 to some number, and I have a rather long lifetime. So let's see if I can break the code and just make first of all, let's make this a little larger. Let's make this 10 times larger. Then I just run it again, and it should be, in this case, it won't create a new file, it will just overwrite it. But you should be able to see now that the decay has, of course, made this go much quicker. Now, let me change this back and make this even maybe a little bit smaller, because I know that let's leave it like this, and let's make this of order 10 to the minus 15. This will make it much more close to the recombination era, but it's still post-recombination era, I believe. Let us look at this and load the result, and you will see that something has happened, but not what I want. Let's just load this. Oh, yes, great. You see, this was a case where you get basically full, excuse me, I will just do this a little bit different color so that you know. This is extremely strong decay, with a lot of decay, and you would basically reionize the medium even at recombination, right? You're putting so much energy in. So let's make this a little longer lived to see what's happening. Then I run again, and I will just plot this again, and hopefully this is now a little bit more, it looks a little bit more like it's not fully reionizing the medium all the time. Now I will just go and decrease this. What this, of course, means is that if you have all dark matter decay with a very high efficiency, then you will, or close to all dark matter decay, then you will have a very significant effect on the ionization history. Now, I'm basically saying a fraction of 10 to minus 5 times 10 to minus 4 of the dark matter is decaying, which is the equivalent of, which is meaning that only a tiny fraction is changing. And you will then see that now this is becoming more like a recombination scenario, which is then having a rather significant pre-recombination, pre-reionization enhancement. Yeah, is there anything else I want to really quickly show? Maybe just a variation of fundamental constants. Again, this is obviously I know something. You guys have heard about the edges result, right? And one of the things that, of course, immediately comes to mind is that you have extra cooling of the matter. And so one of the things that when I heard about this, actually a couple of days before the result came out officially, one of the things that I just did is I said, well, let me change the part of the ODE evaluation where the cooling of the matter is done. So the cooling of the matter, the equation, as you can see, is just this one here. This is really the Compton cooling part and the Hubble expansion. So either you could just add here another cooling term, which, for example, would be this, milli-charged particle interaction, which has a time dependence, which enhances things at late times, right? Or you could just, well, let me just say there's an efficient exchange of energy between the electrons and some other particle all the time. And that would mean that the heat capacity of the medium is actually increasing. So here it is assumed that all the energy that is coming from the photons to the medium, all of this is shared between electrons, the free electrons, and the hydrogen and helium atoms. So that's why you have these factors 1 XE and the fraction of helium atoms. This is basically nothing else than saying all the atomic particles and all the electrons are the same in terms of the temperature, and they all have the same heat capacity. So let me just make sure that I don't have, so I'm going to just load here the temperature which you get in the standard case. Let me just do this one. So the temperature is being output as the last column. You can see all those things in the files. So here is the evolution of the temperature, right? And the evolution of the temperature is at very high redshifts. It's basically like 1 plus z, just because it's tightly coupled to the photons, as you understand. And then around this redshift of 200, 300, it starts decoupling, and there it goes like 1 plus z to the second power, right? And now the edges problem or edges result is that, of course, the amplitude of this absorption feature is twice as big as than you expect, and has a weird shape and all these things, but let's ignore that. Twice as deep means that the temperature of the medium should be twice as low. So something has cooled, if you think in this way, has cooled the medium extra. If you now just increase the heat capacity of the medium, so this is basically equivalent to saying I have another cooling term, but you're assuming that the cooling term is always efficiently coupling to the medium. That was what I was doing when I heard about this. I just multiplied this by several factors. So I said, let's make it twice as efficient, twice as many particles, because nothing else than the number of particles. So add here a factor of 2, which is, of course, I just made that up right now. And then I do my make, and I do the calculation. And then I'm hoping that this will be showing that this goes down a little bit. And then as I said, I was asked by some of my colleagues, and they asked me, is something in standard recombination that you can do? And I said, well, standard recombination, usually you always heat, but I had written a paper on this coupling of dark matter with photons, with electrons and protons, which is actually relevant to the spectral distortion problem at high redshifts. And there we had just done exactly this cooling, so I was immediately saying, well, let's just cool extra. And I made a function of this factor, which I'm just putting here. I made what is the final temperature at redshift of 17, right? So now I just did another increase of this factor, and this factor will now mean it's going down more and more, right? So you see, this is just dropping, and what is the reason? Well, the reason is just because you're having more heat capacity. The heat flow that you get, the decoupling just starts earlier, and that means you have your 1 plus z square scaling starting earlier, and you're basically able to get a lower temperature. Now, that is not to say that this is, of course, the result and the explanation, but that is how you immediately think about these kind of problems. So now I do 10, and 10 was, in fact, what I found was the necessary number to have 17, redshift 17, basically twice as cold in terms of the matter temperature. And that is then giving you this result here. And that would, in principle, allow you to make this dip deeper. But in this case, you would, of course, have a much more broad coupling as well to high redshifts. So this strange shape, especially the steepness and flatness of the core and so on, is very strange to create. And what this flatness of the core might even be indicating, at least that was one of the thoughts that I had, is that it could be a relativistic particle. It should be scaling like 1 plus c because it is basically parallel to the CMB temperature. But that has caveats as well, so don't worry about those statements. It's just to show that there's games you can play, and I think that's one of the things that happened as well, of course, when this observation was being found. I think I will stop there, and I hope I convinced you that Breakfast++ is pretty simple to look at least. You can identify the equations. I must admit that I would like to write them a bit differently, because I think it's easier to think of these coefficients like this instead of this kappa and whatnot. But it is fairly clear what you are looking at is what you normally would be putting in. And if you want to do something in addition, it's easy to add a line there. Okay. Sorry for being longer. I hope this was still helpful, and I stop there. Thank you. And I'm, of course, more than happy to discuss the codes in detail offline, or if you have any questions, ask me. And if you find any bugs, please tell me. And yeah.